Imagine a place in the universe where gravity is so strong that not even light can escape. A place where time slows down and space bends in ways that defy our understanding. This is the realm of black holes, one of the most mysterious and fascinating phenomena in the cosmos. Tonight, we invite you to embark on a cosmic journey into the heart of these enigmatic giants. Together, we'll explore how black holes are born, what happens at their edges, and the secrets they hold within their infinite darkness. From the death of massive stars to the swirling chaos of accretion disks, we'll uncover the extraordinary forces that shape these cosmic wonders. We'll also delve into the unanswered questions that keep scientists awake at night. What lies beyond the event horizon? Could black holes be gateways to other universes? By the end of this journey, you'll not only gain a deeper understanding of black holes, but also feel a sense of awe for the vast and mysterious universe we call home. So, where are you joining us from, and what time is it there? Let's begin our adventure into the mysteries of black holes. Now turning to the origins of these cosmic giants, the birth of a black hole begins with the dramatic end of a massive star. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. This results in a catastrophic event known as a supernova, where the outer layers of the star are violently expelled into space. What remains is the star's core, which undergoes an intense gravitational collapse. If the core's mass is greater than about 3 times the mass of the Sun, the force of gravity becomes so overwhelming that it crushes the core into an infinitely dense point, known as a singularity. This is the heart of a black hole, surrounded by an invisible boundary called the event horizon, where gravity is so strong that nothing, not even light, can escape. Black holes come in different sizes and types, depending on the mass of the star that formed them. Stellar black holes, the most common type, are formed from the remnants of massive stars and typically have masses ranging from about 5 to several dozen times that of the Sun. On the other end of the spectrum are supermassive black holes, which can be millions or even billions of times more massive than the Sun. These colossal entities are found at the centers of galaxies, including our own Milky Way, and their origins remain a topic of intense research. Some theories suggest they grew from the merging of smaller black holes, while others propose they formed directly from the collapse of massive gas clouds in the early universe. The conditions required for a black hole to form are extreme, involving immense gravitational forces and the collapse of a massive object. Yet, despite their mysterious and seemingly destructive nature, black holes play a crucial role in shaping the universe. They influence the motion of stars and galaxies, and their immense gravitational pull can even bend the fabric of space-time itself. As we continue our journey, we'll explore how these cosmic giants operate and the profound questions they raise about the nature of our universe. Now stepping into the enigmatic realm of black holes, let's explore the event horizon, the defining feature that makes these cosmic phenomena so fascinating. Picture the event horizon as the ultimate point of no return, a boundary where the gravitational pull of a black hole becomes so intense that nothing, not even light, can escape its grasp. It's like standing at the edge of a colossal waterfall. Once you cross that edge, There's no turning back. The water pulls you in, just as the black hole's gravity draws everything inward with relentless force. Inside this invisible boundary, the rules of physics as we know them begin to break down. Space and time become so warped that escape is impossible, no matter how much energy or speed an object might have. For an outside observer, an object crossing the event horizon would appear to slow down and eventually fade from view, as the light it emits gets stretched and distorted by the black hole's immense gravity. Yet, for the object itself, the journey across the event horizon would feel instantaneous, marking the moment it becomes part of the black hole's mysterious interior. The event horizon isn't just a physical boundary, it's also a gateway to understanding the extreme conditions that exist within a black hole. By studying it, scientists can glean insights into the nature of gravity, space-time, and the limits of our current understanding of the universe. As we continue our cosmic journey, we'll delve deeper into the heart of these celestial wonders and uncover the profound questions they raise about the fabric of reality. Now venturing deeper into the cosmic abyss, we arrive at the singularity, the enigmatic core of a black hole. Here, gravity becomes infinitely strong, warping space-time beyond comprehension. At this point, the very laws of physics, as we understand them, cease to function, leaving us with more questions than answers. Imagine trying to measure something where the rules of measurement no longer apply. This is the puzzle scientists face when grappling with the singularity. The singularity is thought to be a point of infinite density, where all the mass of the black hole is crushed into an unimaginably small space. It's like compressing an entire mountain into a single grain of sand, but on a scale so extreme that it defies logic. This extreme concentration of matter creates conditions that are simply unfathomable, making the singularity one of the greatest mysteries in modern physics. Studying the singularity poses enormous challenges. Since no information or light can escape a black hole, we have no direct way to observe or measure it. Instead, scientists rely on theoretical models and mathematics to explore its nature. These models suggest that the singularity might be a gateway to entirely new realms of physics, where our current understanding of the universe could be rewritten. The implications of the singularity stretch far beyond black holes themselves. It forces us to confront the limits of our knowledge and raises profound questions about the nature of reality. Could the singularity be a key to unlocking the secrets of the cosmos, or is it a boundary beyond which our understanding cannot pass? As we continue our journey through the mysteries of black holes, the singularity remains a tantalizing enigma, beckoning us to explore the very heart of darkness. Now shifting our gaze to the giants of the cosmos, we encounter supermassive black holes, the colossal anchors at the heart of galaxies. These behemoths are millions, even billions, of times more massive than our Sun, dwarfing the stellar black holes formed from collapsing stars. Unlike their smaller counterparts, supermassive black holes are not the remnants of a single star's death, but are thought to have grown over time, accumulating mass through collisions with other black holes and the steady consumption of surrounding matter. One of the most fascinating aspects of supermassive black holes is their pivotal role in shaping galaxies. They reside at the center of most, if not all, galaxies, including our own Milky Way. Here, their immense gravitational pull doesn't just hold stars in orbit, it influences the very structure and evolution of the galaxy itself. For instance, the energy released from the material spiraling into a supermassive black hole can heat up surrounding gas, preventing it from cooling and forming new stars. This process can effectively regulate star formation, shaping the galaxy's future over billions of years. But the influence of these cosmic giants doesn't stop there. The jets of particles and radiation blasted out from some supermassive black holes can travel vast distances, impacting regions far beyond their host galaxies. These jets can trigger star formation in neighboring galaxies or, conversely, strip away the material needed for new stars to form. It's a delicate balance, where the destructive and creative forces of supermassive black holes intertwine. Despite their immense power, supermassive black holes remain shrouded in mystery. How do they grow so massive in the early universe? What triggers their powerful jets? And what role do they play in the larger tapestry of cosmic evolution? As we continue to unravel these questions, one thing is clear. Supermassive black holes are not just relics of the universe's past but active players in its ongoing story. As we move forward, the next chapter of our journey will explore the smaller, yet equally fascinating, stellar black holes and their place in the cosmic ecosystem. Now turning our attention to the smaller, yet equally intriguing cosmic entities, we explore stellar black holes, the remnants of massive stars that have reached the end of their life cycle. Unlike the supermassive black holes that dominate the centers of galaxies, stellar black holes are born from the dramatic collapse of stars, many times more massive than our Sun. When such a star exhausts its nuclear fuel, it can no longer support its own weight, leading to a catastrophic implosion that compresses its core into an incredibly dense object, a black hole. Stellar black holes are relatively compact, typically ranging from a few to several tens of times the mass of our Sun. Despite their smaller size, their gravitational pull is still immense, strong enough to trap even light itself. Detecting these black holes is a challenge since they don't emit light. However, scientists have developed clever methods to uncover their presence. One of the most effective ways is by observing the behavior of nearby stars. If a star appears to orbit an invisible object, or if its motion suggests it's being tugged by an unseen companion, it's often a clue that a stellar black hole is lurking nearby. Another detection method involves the X-rays emitted by the hot gas swirling into the black hole's accretion disk, a telltale sign of its presence. In the grand cosmic ecosystem, stellar black holes play a vital role. They act as cosmic recyclers, consuming matter and occasionally merging with other black holes, releasing energy in the form of gravitational waves. These ripples in space-time, first detected in 2015, have opened a new window into understanding the universe. Additionally, stellar black holes contribute to the dynamic interplay of matter and energy in their surroundings, influencing the formation of new stars and the evolution of their host galaxies. As we continue to study these remnants of dead stars, they remind us of the intricate connections that bind the cosmos together. From their formation in the fiery collapse of massive stars to their subtle but profound influence on the universe, stellar black holes are a testament to the ever-changing and dynamic nature of space. With this understanding, we now prepare to delve into another mysterious class of black holes, the elusive intermediate black holes, which bridge the gap between stellar and supermassive giants. As we venture deeper into the cosmic enigma of black holes, we encounter a mysterious and elusive class known as intermediate black holes, positioned between the stellar black holes, born from collapsing stars, and the supermassive giants that reside at the hearts of galaxies. These intermediate black holes occupy a unique and puzzling space in our understanding of the universe. Ranging from hundreds to thousands of times the mass of our Sun, they are neither too small nor too large, making them a critical piece in the puzzle of black hole evolution. Detecting intermediate black holes has proven to be a significant challenge. Unlike stellar black holes, which can sometimes be identified by their effects on nearby stars, or supermassive black holes, whose immense presence shapes entire galaxies, intermediate black holes are far more elusive. Their size and location often place them in regions where they don't leave obvious signatures. However, scientists have begun to uncover hints of their existence through indirect methods. For example, the gravitational influence of an intermediate black hole can sometimes be inferred by the unusual motion of stars or gas clouds in its vicinity. Additionally, the X-rays emitted by the hot gas swirling into their accretion disks provide another potential clue. The significance of intermediate black holes lies in their potential role as a missing link in the growth of black holes. How do stellar black holes evolve into the supermassive behemoths we observe today? One leading theory suggests that intermediate black holes could be a stepping stone in this process, growing over time through mergers with other black holes or by accreting vast amounts of matter. Their discovery and study could help us piece together the timeline of black hole formation and shed light on the mechanisms that drive their growth. As astronomers continue to search for these cosmic middleweights, they remind us of the complexities and mysteries that still surround black holes. Intermediate black holes not only challenge our detection capabilities, but also deepen our curiosity about the universe's most intriguing phenomena. With their existence still shrouded in mystery, they hold the key to unlocking new chapters in our understanding of the cosmos. Now, as we turn our attention to the next frontier, we prepare to explore the methods scientists use to uncover these invisible giants, a journey into the science of black hole detection. Now, as we delve into the fascinating science of detecting black holes, we uncover the ingenious methods scientists use to observe these invisible cosmic wonders. One of the primary techniques involves studying the behavior of nearby stars. When a star orbits an unseen object, its movement can betray the presence of a black hole. By tracking these orbital patterns and calculating the gravitational forces at play, astronomers can infer the existence and even estimate the mass of the black hole. This method has been particularly effective in identifying stellar black holes. Another powerful tool in the detection arsenal is gravitational lensing. This phenomenon occurs when the immense gravity of a black hole bends the light from objects behind it, acting like a cosmic magnifying glass. By observing how light from distant stars or galaxies is distorted, scientists can map the presence and properties of black holes, even when they don't emit any light of their own. Gravitational lensing has opened a new window into studying black holes, especially those that are otherwise hidden from view. A third key method involves detecting X-ray emissions from accretion disks. As gas and dust spiral into a black hole, they heat up to extreme temperatures, emitting high-energy X-rays. Space-based telescopes equipped with X-ray sensors can capture this radiation, providing direct evidence of a black hole's presence. This technique has been instrumental in discovering supermassive black holes at the centers of galaxies, as well as more elusive intermediate black holes. Each of these methods offers a unique perspective, allowing scientists to piece together a more complete picture of black holes. By combining observations from different techniques, researchers can confirm their findings and uncover new insights into these enigmatic objects. As we continue to refine our detection methods, we move closer to unraveling the secrets of black holes and their role in shaping the universe. Next, we'll explore the swirling disks of matter that surround black holes, known as accretion disks, and how they reveal even more about these cosmic mysteries. Now turning to the swirling rings of matter that encircle black holes, we encounter accretion disks, often referred to as the cosmic buffet. These disks are formed as gas, dust, and other material are drawn toward the black hole by its immense gravitational pull. Instead of falling directly into the black hole, this matter begins to orbit around it, forming a flattened, rotating disk. The intense friction and heat generated within these disks cause the material to glow brightly, emitting radiation across the electromagnetic spectrum. Accretion disks are not just spectacular to observe, they also serve as vital tools for understanding black holes. The radiation they emit, particularly in the form of X-rays, provides scientists with crucial information about the black hole's properties, such as its mass, spin, and rate of consumption. By analyzing this radiation, astronomers can determine how quickly material is being pulled into the black hole, and even map the structure of the disk itself. Interestingly, not all accretion disks are the same. Their size, brightness, and behavior can vary depending on the type of black hole they surround. For instance, the accretion disks around supermassive black holes at the centers of galaxies can span vast distances and shine with incredible intensity, often outshining the entire galaxy. In contrast, those around smaller stellar black holes may be more compact and less luminous, but still reveal important details about these cosmic remnants. As we study these cosmic whirlpools, we gain deeper insights into the dynamic processes that occur near black holes. They not only illuminate the hidden nature of these enigmatic objects, but also play a key role in shaping their surroundings. Next, we'll explore the powerful jets of particles that shoot out from some black holes, a phenomenon that adds another layer of intrigue to these cosmic mysteries. Now delving into another extraordinary phenomenon tied to black holes, we encounter the mesmerizing jets of particles that blast outward at nearly the speed of light. These jets, often described as cosmic particle cannons, are among the most energetic events in the universe. They originate from the regions near the poles of supermassive black holes, where intense magnetic fields and the spinning motion of the black hole combine to launch material into space with unimaginable force. The formation of these jets begins within the accretion disk. As material spirals toward the black hole, some of it gets funneled along the magnetic field lines toward the poles. Instead of being consumed by the black hole, this material is accelerated outward in two narrow, focused streams. The process is so powerful that it propels particles across vast distances, sometimes extending far beyond the boundaries of the host galaxy. The impact of these jets on their surroundings is profound. When they collide with interstellar gas and dust, they can trigger the formation of new stars or, conversely, halt star formation by heating and dispersing the material. They also play a role in shaping the structure of galaxies, influencing their evolution over billions of years. In some cases, these jets are so energetic that they can be observed from billions of light years away, serving as beacons that help astronomers study the early universe. Understanding these cosmic jets not only sheds light on the behavior of black holes, but also provides insights into the interconnected nature of the universe. As we continue to explore these powerful phenomena, we'll uncover more about how black holes, despite their destructive reputation, also act as cosmic architects, shaping the cosmos in ways we are only beginning to comprehend. Now shifting our gaze to another groundbreaking discovery, let's explore the phenomenon of gravitational waves, ripples in the very fabric of space-time itself. These waves are created by some of the most violent events in the universe, such as the collision of black holes. When two black holes spiral toward each other and eventually merge, they send out a shock wave that distorts space-time, much like a pebble dropped into a still pond sends out ripples. However, these ripples travel at the speed of light and carry with them the echoes of the cataclysmic event that birthed them. The detection of gravitational waves is a monumental achievement in science. Using highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, scientists have been able to measure these tiny distortions in space-time. The first detection in 2015 marked a new era in astronomy, allowing us to observe the universe in a completely different way. Unlike light or other electromagnetic waves, gravitational waves pass through matter unimpeded, giving us a direct glimpse into events that would otherwise remain hidden. The significance of these discoveries cannot be overstated. Gravitational waves have confirmed key predictions of Albert Einstein's theory of general relativity and opened a new window into the cosmos. They allow us to study black holes and neutron stars with unprecedented precision, revealing details about their masses, spins, and the dynamics of their collisions. Moreover, these observations help us understand the nature of space-time itself, shedding light on the fundamental forces that shape our universe. Through the study of gravitational waves, we're not just observing the universe, we're listening to it. Each detection tells a story, from the birth of black holes to the formation of galaxies billions of years ago. As we continue to refine our ability to detect these ripples, we'll uncover even more about the intricate dance of the cosmos and our place within it. Now turning to one of the most mind-bending effects of black holes, let's explore how their immense gravity warps time itself. Near a black hole, time doesn't flow as it does here on Earth. Instead, it slows down, a phenomenon known as time dilation. This happens because the black hole's gravity is so strong that it bends the fabric of space-time, stretching time in ways that defy our everyday experience. This isn't just theoretical, it's a direct consequence of Einstein's theory of general relativity. To understand this better, picture the twin paradox. Imagine two twins, one staying on Earth and the other traveling close to a black hole. The twin near the black hole would experience time passing much more slowly than their sibling on Earth. After what feels like a few hours to the spacefaring twin, they might return to Earth to find that decades have passed for their sibling. This bizarre effect is a result of the intense gravitational field of the black hole, which slows time for anyone or anything near it. Time dilation near a black hole isn't just a fascinating thought experiment. It has real implications for how we understand the universe. For example, if we could observe someone falling into a black hole, we'd see their movements slow down until they seemingly freeze at the event horizon. This isn't because they've stopped moving, but because time itself has slowed to a crawl from our perspective. This phenomenon also raises intriguing questions about the nature of time and reality. Are time and space truly as fixed as we perceive them, or are they more fluid, shaped by the forces of gravity? Black holes, with their ability to warp time, challenge our understanding and invite us to rethink the very fabric of existence. As we ponder these questions, we're reminded that the universe is far stranger and more wondrous than we could ever imagine. Now shifting our focus to another astonishing effect of black holes, let's delve into a process as fascinating as it is terrifying: spaghettification. Imagine you're floating in space, approaching a black hole. As you get closer, something extraordinary begins to happen. The gravitational pull of the black hole isn't uniform. It's stronger at your feet than at your head. This difference in force stretches you out, pulling you longer and thinner like a piece of spaghetti. This is spaghettification, and it's one of the most dramatic ways a black hole can interact with matter. The process begins as you cross the event horizon, the point of no return. The black hole's immense gravity starts to pull on every part of you, but because your feet are slightly closer to the center, they're tugged more forcefully than your head. This tidal force, the difference in gravity, stretches you out, elongating your body into a thin, noodle-like shape. It's not just a visual effect. Every atom in your body would be pulled apart in this extreme gravitational field. To make this more relatable, think of a piece of taffy being pulled from both ends. As the forces increase, the material becomes thinner and thinner until it eventually breaks. In the case of spaghettification, the stretching continues until the object is reduced to a stream of particles, spiraling into the black hole. This isn't just a theoretical idea. It's a real physical process that would happen to anything unfortunate enough to get too close. Spaghettification isn't just a mind-boggling concept. It also highlights the sheer power and strangeness of black holes. These cosmic entities don't just swallow matter. They transform it in ways that defy our everyday understanding of physics. As we explore these extreme phenomena, we're reminded once again of the universe's ability to both awe and unsettle us, pushing the boundaries of what we thought was possible. With this vivid mental image in mind, let's now turn to another intriguing aspect of black holes, the mysterious radiation they emit, known as Hawking radiation, which suggests that even these gravitational giants aren't entirely black. Now shifting our focus to another groundbreaking discovery, let's explore the idea that black holes aren't as dark as they seem. Stephen Hawking, one of the greatest minds in physics, proposed a theory that changed the way we think about these cosmic giants. According to Hawking, black holes can actually emit radiation, a phenomenon now known as Hawking radiation. This remarkable idea suggests that black holes aren't entirely black after all, but rather they slowly lose energy and mass over time. Hawking radiation arises from the strange behavior of particles at the edge of a black hole's event horizon. In the quantum world, particles and their antimatter counterparts are constantly popping into existence and annihilating each other. Normally, these pairs vanish almost instantly, but near a black hole, one particle can fall in while the other escapes, carrying away energy. Over incredibly long timescales, this process causes the black hole to lose mass and eventually evaporate completely. This discovery has profound implications for the lifespan of black holes. While larger black holes can exist for billions or even trillions of years, smaller ones could evaporate much faster. Hawking radiation also challenges the idea that black holes are eternal, suggesting instead that they have a finite existence. This raises fascinating questions about what happens to all the information that falls into a black hole. Does it disappear forever, or is it somehow preserved in the radiation? This question remains one of the greatest mysteries in physics. Hawking radiation not only deepens our understanding of black holes, but also bridges the gap between quantum mechanics and general relativity. It's a testament to the power of human curiosity and the endless surprises the universe has in store. As we continue to unravel the secrets of black holes, we're reminded that even the darkest corners of space can reveal unexpected glimmers of light. With this in mind, let's now turn to another intriguing concept: white holes, the hypothetical opposites of black holes. Now stepping into the realm of theoretical physics, we encounter a fascinating counterpart to black holes: white holes. While black holes are known for their immense gravitational pull, trapping everything that crosses their event horizon, white holes are thought to do the exact opposite. Instead of consuming matter and energy, these hypothetical objects are believed to expel them, acting as cosmic fountains rather than cosmic vacuums. The idea of white holes emerges from the same equations that describe black holes, suggesting they are essentially the reverse of their darker siblings. In theory, a white hole would be a region of space where matter and energy can escape, but nothing can enter. Imagine a black hole's event horizon in reverse, a boundary that only allows outward flow. While black holes are supported by observational evidence, white holes remain purely theoretical, existing as intriguing possibilities in the minds of physicists. One of the most compelling aspects of white holes is their potential connection to the Big Bang. Some scientists speculate that the early universe could have resembled a white hole, with energy and matter bursting outward in a rapid expansion. This idea bridges the gap between the birth of the universe and the behavior of these mysterious cosmic objects. However, white holes also pose significant challenges to our understanding of physics. For instance, they would require a mechanism to prevent matter from falling in, which contradicts our current understanding of gravity. Despite the lack of direct evidence, white holes continue to spark curiosity and debate in the scientific community. They serve as a reminder that the universe is full of untapped mysteries, challenging us to think beyond the boundaries of what we know. As we ponder the possibility of white holes, we're invited to explore the endless creativity of physics and the profound questions it seeks to answer. With this intriguing concept in mind, let's now venture into another fascinating idea: wormholes, the hypothetical tunnels through space-time that could connect distant parts of the universe. As we delve deeper into the realm of space-time mysteries, we arrive at the intriguing concept of wormholes. These hypothetical tunnels, often depicted in science fiction, are theorized to bridge distant parts of the universe, or even connect entirely different universes. Imagine a shortcut through the vast cosmic fabric, allowing travel across unimaginable distances in the blink of an eye. This idea stems from Einstein's theory of general relativity, which suggests that spacetime can bend and twist in ways that create these potential passages. Wormholes, also known as Einstein-Rosen bridges, are solutions to the equations of general relativity, but they remain purely theoretical. To visualize a wormhole, picture a sheet of paper with 2 points marked on opposite ends. Folding the paper so the points touch creates a direct connection, an analogy for how a wormhole could link two distant locations in space-time. However, the existence of such shortcuts poses significant challenges. For a wormhole to be traversable, it would require exotic matter with negative energy to stabilize it, something we haven't discovered yet. One of the most fascinating aspects of wormholes is their potential to connect not just space, but also time. This raises the tantalizing possibility of time travel, where entering a wormhole could lead to a different era in the past or future. However, this idea also comes with paradoxes, such as the famous grandfather paradox, which questions what would happen if someone traveled back in time and altered their own history. While wormholes remain speculative, they continue to inspire both scientists and storytellers alike. They challenge us to rethink the boundaries of space, time, and the very fabric of reality. As we ponder these cosmic shortcuts, we're reminded of the boundless creativity of theoretical physics and the endless questions it seeks to unravel. With this mind-bending concept in place, let's now turn to another profound question: the black hole information paradox, and what happens to the information that falls into these cosmic enigmas. Now turning to one of the most perplexing questions in modern physics, we encounter the black hole information paradox. This paradox centers around the fate of information that falls into a black hole. According to our current understanding of physics, information like the properties of particles can never be destroyed. Yet, black holes, with their immense gravitational pull, seem to challenge this fundamental principle. Once something crosses the event horizon, it's as if it's lost forever, leaving us to wonder what happens to that information. The heart of the paradox lies in the clash between two powerful theories: quantum mechanics and general relativity. Quantum mechanics insists that information must be preserved, while general relativity suggests that it's irretrievably lost within a black hole. This contradiction has puzzled scientists for decades, as it implies a gap in our understanding of the universe's most basic laws. Stephen Hawking brought this paradox into sharper focus with his discovery of Hawking radiation. Black holes, he proposed, emit radiation over time and can eventually evaporate. But if a black hole evaporates, what happens to the information it once contained? Does it vanish into the void, or is it somehow encoded in the radiation? This question remains unresolved, making it one of the greatest unsolved problems in physics. Some theories suggest that the information might be stored on the black hole's event horizon, encoded in a way we don't yet understand. Others propose that it's released back into the universe through Hawking radiation, albeit in a scrambled form. Still, a definitive answer remains elusive, highlighting the need for a deeper theory that unifies quantum mechanics and general relativity. As we grapple with this paradox, we're reminded of the vast mysteries that black holes continue to hold. They challenge our understanding of reality, pushing the boundaries of science and imagination. With this enigma still unsolved, our journey into the cosmos takes us next to another fascinating concept: primordial black holes, relics of the Big Bang itself. Now shifting our gaze to the very dawn of the universe, we encounter the intriguing concept of primordial black holes. Unlike the black holes formed from collapsing stars, primordial black holes are thought to have emerged in the chaotic moments following the Big Bang itself. These ancient relics are hypothesized to have formed from the intense density fluctuations in the early universe, where pockets of matter condensed into black holes before stars or galaxies even existed. What makes primordial black holes so fascinating is their potential role in solving some of cosmology's biggest mysteries. One of the most compelling ideas is that they could contribute to the elusive substance known as dark matter. While dark matter makes up a significant portion of the universe's mass, it remains invisible to us, detectable only through its gravitational effects. Primordial black holes, if they exist in sufficient numbers, might account for at least a portion of this missing mass, offering a tantalizing clue to the nature of dark matter. The search for primordial black holes is ongoing, with scientists exploring various methods to detect them. Since they would be much smaller than stellar or supermassive black holes, some potentially as small as an atom, they might emit detectable signals, such as bursts of radiation, as they evaporate through Hawking radiation. Alternatively, their gravitational influence could bend light from distant objects, a phenomenon known as gravitational lensing, providing indirect evidence of their existence. If primordial black holes are confirmed, they would not only deepen our understanding of the early universe, but also open new avenues for exploring the interplay between cosmology and particle physics. They could help bridge the gap between the microcosm of quantum mechanics and the macrocosm of general relativity, offering insights into the universe's fundamental workings. As we ponder the possibility of these ancient black holes, we're reminded of how much the universe still has to reveal. Every discovery, every theory, brings us closer to unraveling the mysteries of our cosmic origins. With this in mind, our journey now takes us to the next frontier, where black holes meet another profound puzzle: the tension between quantum mechanics and general relativity. Now turning to one of the most profound challenges in modern physics, we find ourselves at the crossroads of two monumental theories: general relativity and quantum mechanics. General relativity, Albert Einstein's groundbreaking work, describes the universe on a grand scale, explaining how massive objects like black holes warp the fabric of space and time. Quantum mechanics, on the other hand, governs the behavior of the tiniest particles, revealing a world of probabilities and uncertainties. While both theories have been incredibly successful in their own domains, they seem fundamentally incompatible when it comes to understanding black holes. At the heart of this clash is the singularity, the point within a black hole where gravity becomes infinitely strong and the laws of physics, as we know them, break down. General relativity predicts this singularity, but it cannot explain what happens there. Quantum mechanics, meanwhile, suggests that information cannot simply disappear, yet black holes appear to defy this principle by seemingly destroying everything that falls into them. This contradiction lies at the core of the black hole information paradox, a puzzle that has stumped physicists for decades. Scientists are working tirelessly to bridge this gap, exploring theories like quantum gravity and string theory, which attempt to unify these two frameworks. One promising idea is the concept of Hawking radiation, proposed by Stephen Hawking, which suggests that black holes emit particles and slowly lose mass over time. This process hints at a possible resolution, as it implies that black holes might not destroy information entirely, but instead encode it in subtle ways. Another avenue of research focuses on the holographic principle, which posits that all the information about what falls into a black hole could be stored on its surface, much like a hologram. This idea challenges our conventional understanding of space and dimensionality, offering a radical new perspective on the nature of black holes. As we delve into these cutting-edge theories, it's clear that the quest to reconcile general relativity and quantum mechanics is not just about understanding black holes. It's about uncovering the fundamental laws that govern the universe itself. Every discovery, every insight, brings us closer to a unified theory that could revolutionize our understanding of reality. With this in mind, our journey continues, exploring how black holes intersect with another captivating concept: their portrayal in popular culture. Now shifting our gaze from the complexities of theoretical physics, we step into the fascinating world of popular culture, where black holes have captured the imagination of storytellers and audiences alike. In movies, books, and television, black holes often serve as gateways to adventure, mystery, and even existential reflection. From Hollywood blockbusters like Interstellar to science fiction classics like Event Horizon, these cosmic phenomena have been depicted in ways that range from scientifically inspired to wildly speculative. While these portrayals may not always align with the latest discoveries, they play a crucial role in shaping how people perceive and relate to black holes. One of the most iconic cinematic representations of black holes is in the film Interstellar, where a supermassive black hole named Gargantua, is rendered with stunning visual accuracy, based on the input of astrophysicist Kip Thorne. The film's depiction of time dilation near a black hole, while dramatized, introduced audiences to the mind-bending effects of extreme gravity. Similarly, science fiction literature has long used black holes as narrative devices, from Arthur C. Clarke's Rendezvous with Rama to the works of Isaac Asimov, where they often symbolize the unknown and the infinite. Beyond their role in storytelling, these portrayals have a profound impact on public perception. For many, fictional depictions of black holes serve as their first introduction to these cosmic wonders, sparking curiosity and inspiring a deeper interest in science. However, they can also lead to misconceptions, such as the idea that black holes are cosmic vacuum cleaners, or that they can transport you to another dimension. While these ideas make for compelling fiction, they often oversimplify or exaggerate the true nature of black holes. Despite these inaccuracies, the influence of popular culture cannot be underestimated. It has the power to make complex scientific concepts accessible and engaging, encouraging people to explore the real science behind the fiction. Moreover, it creates a bridge between scientists and the public, opening up conversations about the mysteries of the universe and the importance of scientific discovery. As we continue to unravel the secrets of black holes, it's worth reflecting on how these cultural depictions shape our understanding and fuel our fascination with the cosmos. With this in mind, we turn our attention to the largest black hole ever discovered, a true testament to the awe-inspiring scale of these cosmic giants. Now focusing our attention on one of the most astonishing discoveries in the cosmos, we turn to the largest black hole ever found. Known as TON 618, this colossal structure resides in the heart of a distant galaxy, shining brightly as a quasar due to the intense radiation emitted by the material swirling around it. With a mass estimated at more than 66 billion times that of our Sun, TON 618 is not just a marvel of nature, but a reminder of the sheer scale of the universe. Located more than 10 billion light-years away, this massive black hole was detected through a combination of techniques, including observations of its surrounding accretion disk and the effects of its gravitational pull on nearby stars. Astronomers used powerful telescopes, such as the Hubble Space Telescope and ground-based observatories, to measure the speed of the gas and stars orbiting the black hole, allowing them to calculate its enormous mass. What makes this discovery even more remarkable is that TON 618 challenges our understanding of how black holes grow. Scientists believe that supermassive black holes like this one formed in the early universe, but the exact mechanisms that allowed them to reach such staggering sizes remain a mystery. Some theories suggest they grew rapidly by merging with other black holes or by consuming vast amounts of gas and dust during a period of intense cosmic activity. This black hole's detection also highlights the incredible advancements in technology and methodology that have made such discoveries possible. By studying objects like TON 618, astronomers gain valuable insights into the formation and evolution of galaxies, as well as the role black holes play in shaping the universe. As we wrap up this exploration, it's worth reflecting on the grandeur of Ton 618 and what it represents. This cosmic giant is not just an astronomical curiosity, but a window into the extreme forces that govern our universe. With each discovery like this, we come one step closer to unlocking the secrets of the cosmos and understanding our place within it. Shifting our gaze to another cosmic mystery, we now explore the intriguing connection between black holes and dark matter. While black holes are known for their immense gravitational pull, dark matter remains one of the universe's most elusive enigmas, invisible yet accounting for a significant portion of the cosmos's mass. Scientists have long wondered if these two phenomena could be linked, and recent theories suggest that black holes might hold clues to understanding dark matter. One compelling idea is that primordial black holes, which may have formed in the early universe, could be a component of dark matter. These ancient black holes, smaller than the ones we observe today, might have existed in vast numbers, contributing to the unseen mass that influences the motion of galaxies. If true, this would mean that black holes are not just cosmic vacuum cleaners, but also key players in the structure and evolution of the universe. Another theory explores the possibility that dark matter particles interact with black holes in ways we are yet to fully understand. For instance, dark matter could accumulate around black holes, creating dense halos that enhance their gravitational effects. This interaction might explain why some galaxies rotate faster than expected, as the combined influence of black holes and dark matter could be altering their dynamics. As we continue to study black holes, their potential connection to dark matter opens up new avenues for research. By observing how black holes behave and how they affect their surroundings, scientists hope to uncover more about the nature of dark matter and its role in the cosmos. These investigations could bring us closer to solving one of the greatest puzzles in modern astrophysics. This exploration reminds us that the universe is filled with hidden connections, waiting to be discovered. As we piece together the relationship between black holes and dark matter, we not only deepen our understanding of these phenomena, but also take another step toward unraveling the mysteries of the cosmos. Now shifting our focus to the realm of myths and misconceptions, let's dive into some of the most common misunderstandings about black holes. One of the biggest myths is that black holes act like cosmic vacuum cleaners, sucking up everything in their path. While it's true that their gravitational pull is incredibly strong, they don't indiscriminately consume everything around them. Objects need to cross the event horizon, the point of no return, to be pulled in. Otherwise, they can orbit a black hole just as planets orbit a star. Another widespread belief is that black holes are immortal and will last forever. However, thanks to the groundbreaking work of Stephen Hawking, we now know that black holes can emit radiation and slowly lose mass over time. This process, known as Hawking radiation, means that black holes can eventually evaporate, though it would take an unimaginably long time for even the smallest ones to disappear completely. Some people also think that black holes are portals to other universes or dimensions. While this idea is fascinating and has been explored in science fiction, there's no scientific evidence to support it. Black holes are incredibly dense objects with extreme gravity, but they don't function as gateways to other realms. Lastly, there's a misconception that black holes are rare, and only exist in distant parts of the universe. In reality, they're more common than you might think. Supermassive black holes reside at the center of most galaxies, including our own Milky Way, and smaller stellar black holes are scattered throughout the cosmos. By debunking these myths, we can better appreciate the true nature of black holes. They're not the menacing, all-consuming monsters often portrayed in popular media, but rather fascinating and complex objects that continue to challenge our understanding of the universe. Now turning to a question that sparks both curiosity and imagination: could life exist near black holes? At first glance, the idea seems impossible. Black holes are known for their intense gravity, radiation, and extreme environments that would obliterate most known forms of life. Yet, when we consider the potential energy sources and unique conditions surrounding these cosmic giants, the possibility becomes less far-fetched. One key factor to explore is the accretion disk, the swirling ring of gas and dust that orbits a black hole. These disks emit immense amounts of radiation and heat, creating environments that could theoretically support chemical reactions necessary for life. While the conditions would be harsh, some extremophiles on Earth thrive in similarly hostile environments, such as deep-sea hydrothermal vents or acidic hot springs. Could life adapt to the intense radiation and heat of an accretion disk? Another intriguing possibility lies in tidal forces. As objects approach a black hole, they experience spaghettification, stretching into thin strands due to gravity. While this might seem fatal, some scientists speculate that tidal forces could also create regions of stability where life might find a foothold. These zones, though rare, could offer a delicate balance between the black hole's pull and the energy it provides. Finally, the concept of energy harvesting comes into play. Life near a black hole might not rely on sunlight or organic matter as we do. Instead, it could harness the immense energy emitted by the accretion disk, or even the black hole's rotation. Theoretical models suggest that advanced civilizations might one day use black holes as power sources, but even simpler forms of life could evolve to utilize these energy streams in creative ways. While the idea of life near black holes remains speculative, it challenges us to think beyond our current understanding of biology and physics. It reminds us that the universe is full of possibilities, and even in the most extreme environments, life might find a way to thrive. As we continue to explore the mysteries of black holes, this question will remain a fascinating topic of debate and discovery. As we venture deeper into the mysteries of black holes, let's explore a concept that blurs the line between science and science fiction: the idea that black holes could serve as gateways to other dimensions or even entire universes. This fascinating theory ties into the concept of the multiverse, a hypothetical collection of parallel universes that exist alongside our own. Could black holes be the bridges connecting these realms? One of the most intriguing possibilities is the role of wormholes, theoretical tunnels through space-time that could connect distant regions of the universe, or even different universes altogether. While wormholes remain unproven, some scientists suggest that the intense gravitational forces within black holes might create the conditions necessary for these cosmic shortcuts to form. Imagine a black hole as a doorway, not just to oblivion, but to an entirely new reality. Another angle to consider is the singularity at the center of a black hole, where the laws of physics as we know them break down. In this realm of infinite density, exotic phenomena could occur, such as the creation of new space-time fabrics, or the formation of entirely new universes. Some theories propose that our universe itself might have originated from a singularity in another universe's black hole, sparking the Big Bang that birthed everything we know. The multiverse theory also raises questions about the nature of reality. If black holes do act as portals, what would these other universes be like? Could they have entirely different physical laws, dimensions, or even forms of existence? While these ideas remain speculative, they challenge us to rethink our understanding of the cosmos and the boundaries of possibility. As we ponder these cosmic mysteries, one thing becomes clear: black holes are not just destructive forces, but potential keys to unlocking some of the universe's greatest secrets. Whether as gateways to other worlds or the cradles of new realities, they continue to inspire wonder and fuel our quest for knowledge. Now, as we shift our gaze toward the horizon of discovery, let's consider what the future holds for black hole research. Scientists are on the brink of unlocking new secrets, thanks to groundbreaking technologies and ambitious missions designed to probe deeper into these cosmic enigmas. One of the most exciting tools in this quest is the Event Horizon Telescope, a global network of radio telescopes that works together to capture images of black holes. In 2019, this collaboration made history by producing the first ever image of a black hole's event horizon, located in the galaxy Messier 87. This achievement not only confirmed decades of theoretical predictions, but also opened the door to further exploration. Future upgrades to the Event Horizon Telescope aim to produce even sharper images, allowing scientists to study the intricate details of black holes and their surrounding environments. Space missions are also playing a pivotal role in advancing our understanding. Projects like the Laser Interferometer Space Antenna, or LISA, are set to detect gravitational waves with unprecedented precision. By observing the ripples in space-time caused by merging black holes, LISA could provide insights into their formation, evolution, and the fundamental nature of gravity itself. On the theoretical front, researchers are exploring new models to reconcile the mysteries of black holes with the laws of quantum mechanics. One area of focus is the black hole information paradox, which questions what happens to the information that falls into a black hole. Solving this puzzle could revolutionize our understanding of how information is preserved in the universe. Another promising avenue is the study of primordial black holes, which are thought to have formed in the early moments of the universe. If detected, these ancient objects could shed light on the conditions of the Big Bang and even help explain the nature of dark matter. As we look ahead, the collaboration between observation, experimentation, and theory promises to bring us closer to unraveling the secrets of black holes. Each new discovery not only deepens our understanding of these cosmic phenomena, but also challenges us to rethink our place in the vast and mysterious universe. As we venture into the vast unknowns of the cosmos, let's explore how black holes might shape the ultimate destiny of the universe itself. These mysterious objects, born from the collapse of massive stars, could hold the key to understanding how the universe evolves over billions of years. One compelling theory is the Big Crunch, a scenario where the universe, after expanding for eons, begins to contract under the pull of gravity. In this model, black holes could play a central role, their immense gravitational forces accelerating the collapse. As galaxies are drawn closer together, black holes would merge, growing larger and more powerful until the universe itself is consumed in a final cosmic crunch. On the other end of the spectrum lies the theory of heat death, where the universe continues to expand indefinitely, growing colder and more chaotic over time. In this scenario, black holes would eventually evaporate due to a process known as Hawking radiation, slowly releasing their energy into the void. Over unimaginable timescales, even the largest black holes would fade away, leaving behind a universe devoid of energy and structure. Between these two extremes, black holes also influence the formation and evolution of galaxies, which in turn shape the large-scale structure of the cosmos. Supermassive black holes, found at the centers of galaxies, can regulate star formation and even determine the fate of entire galactic systems. Their interactions with surrounding matter create feedback loops that either foster new stars or stifle their birth, leaving a lasting imprint on the universe's development. As scientists continue to study these cosmic giants, they uncover clues about the universe's past, present, and future. Black holes, once thought to be simple destroyers, are now understood as dynamic forces that shape the cosmos in profound ways. Whether driving the universe toward a fiery collapse or a cold, silent end, black holes remain at the heart of one of the greatest questions in science. What is the ultimate fate of our universe? With each discovery, we move closer to answering this question, piecing together the story of the cosmos and our place within it. The journey is far from over, and black holes continue to challenge and inspire us, inviting us to explore the mysteries that lie at the edge of existence. Now, let's take a moment to step into the shoes, or rather the spacesuit, of an imaginary traveler. Picture yourself drifting through the silence of space, approaching the edge of a black hole. At first, everything seems calm. The black hole looms in the distance, a vast, dark sphere surrounded by a faint, glowing ring of light known as the accretion disk. As you inch closer, the pull of gravity begins to tug on your ship, gently at first, but steadily growing stronger. As you cross the event horizon, the boundary beyond which nothing can escape, something strange happens. Time begins to slow down. If you could look back at the universe outside, you'd see the stars and galaxies stretch and warp, their light bending into bizarre shapes. Meanwhile, the black hole's immense gravity starts to stretch your body in a process scientists call spaghettification. Your feet, pulled by the stronger gravitational force near the black hole's center, would stretch away from your head, elongating you into a thin strand. The journey inward becomes increasingly surreal. The light from the accretion disk grows brighter, swirling around you like a cosmic whirlpool. You'd feel an overwhelming sense of isolation, knowing that no signal, no cry for help, could ever reach the outside universe. Yet, in this moment of intense gravity, the laws of physics as we know them begin to break down. The singularity at the heart of the black hole remains a mystery, a point where matter is crushed into infinite density. What lies beyond the singularity? Could it be a gateway to another universe, a tunnel through space-time, or simply the end of existence? As you approach it, the question lingers, unanswered and profound. This thought experiment isn't just about the physics of black holes. It's about the limits of human understanding and our place in the vast, enigmatic cosmos. What would you feel, think, or discover in those final moments? The experience is both terrifying and awe-inspiring, a reminder of the endless mysteries that black holes hold. Now, as we leave this imaginary journey behind, let's turn our attention to the next chapter of our exploration, where we'll delve into the cutting-edge technologies and missions that are bringing us closer to understanding these cosmic enigmas. As we bring our cosmic journey to a close, let's reflect on the incredible mysteries we've explored today. From the birth of black holes through the collapse of massive stars, to the mind-bending concepts of event horizons, singularities, and Hawking radiation, these cosmic phenomena challenge everything we think we know about the universe. We've marveled at the immense power of supermassive black holes, shaping galaxies, and pondered the existence of primordial black holes from the dawn of time. We've even ventured into the realm of theoretical possibilities like wormholes and white holes, imagining what might lie beyond the known limits of space and time. Yet, for all that we've uncovered, black holes remain shrouded in mystery. What happens inside a singularity? Could black holes hold the key to understanding dark matter or even the multiverse? These questions remind us that the universe is far more complex and fascinating than we can currently comprehend. Every discovery opens new doors, and every unanswered question invites us to keep exploring. So, as we conclude, I leave you with this thought. What wonders do you think we'll uncover next in our quest to understand the cosmos? The journey doesn't end here. It's only just beginning. I encourage you to keep looking up, keep asking questions, and keep marveling at the infinite mysteries of the universe. If you've enjoyed this journey, don't forget to like, subscribe, and hit the notification bell so you never miss an adventure into the cosmos. Until next time, keep exploring. you.